Remember Peter Pan's directions to Neverland? Second star to the left and straight on till morning. This whimsical idea mirrors the exciting possibilities of seemingly instantaneous interstellar travel through the undisturbed fabric of space-time. Our adventure begins with Einstein's theory of general relativity, which explains how mass and energy warp the fabric of space-time. According to Einstein, mass tells space-time how to curve, and space-time tells mass how to move, setting the stage for a universe where distances and speeds can be perceived differently. In areas of minimal space-time curvature, away from the heavy gravitational pull of stars or planets, space-time is less distorted. It's here that we encounter the phenomenon of enhanced speed perception, where travel speeds can feel vastly increased. Einstein's equations also elucidates gravitational time dilation, showing us how time stretches or shrinks in the presence of gravity. According to Einstein's general relativity, what we perceive as the force of gravity actually comes from curves in space-time caused by massive objects like stars and planets. When objects like Earth or the Sun are present, they curve space-time significantly, which affects how we move and even how time passes around us. This effect is called gravitational time dilation. Near a massive object like our Sun, time actually moves slower compared to areas farther away where space-time is flatter. Now, here's where it gets really interesting for space travel. As a spacecraft moves away from massive celestial bodies into areas where space-time is less curved, the effects of gravitational time dilation decrease. So, if you were on a spaceship moving through these flatter areas, the journey could actually feel a lot quicker than the same journey made closer to massive bodies where time dilates more. Now let's dive deeper. The Schwarzschild solution to Einstein's equations provides a clear depiction of space-time around a spherical mass. This solution is instrumental in describing gravitational time dilation. It illustrates how time dilates differently based on proximity to a mass. This concept becomes pivotal in deriving the implications for perceived travel speeds. Applying these principles, we derive equations that predict how space-time curvature influences perceived travel speeds. These insights reveal why travelers might experience increased speeds as they navigate through flatter regions of space. Drawing from this foundation, we derive a novel travel perception equation. This integral calculates the proper time experienced by a traveler, considering the change in gravitational potential along the path. This model offers an exciting perspective on potential anomalies in travel time perception as distances from mass sources increase. We've discussed how this affects our perception of time, especially in the context of space travel. Moving into emptier areas of space, where space-time is less curved, could make interstellar journeys feel a lot quicker due to the decreased effects of time dilation. Now, how do we test these theories? We detail how advancements in precision timekeeping and astronomical observations could empirically test our derived equations. The potential for observing these effects with current and soon-to-be-developed technologies is critically assessed. Finally, using numerical relativity, we simulate the travel paths under various space-time curvatures to visually and quantitatively predict the outcomes suggested by our theoretical models. These simulations aim to bridge the gap between theoretical predictions and observable phenomena. In summary, the interplay of mass, energy, and space-time curvature has profound implications for our perception of interstellar travel speeds. By understanding these dynamics, we open up new perspectives on navigating the cosmos and push the boundaries of theoretical physics. So, the next time you look up at the night sky, remember, space isn't just about vast distances. It's also about time, and how we perceive it can change based on where we are in the universe. The journey through the cosmos might someday feel as swift as flying to Neverland.